So after the nice diplomatic talk by John Martinez, we have now the chance to dig into more details of our qubits. We have very lucky to have 4 experts in 4 different types of qubits. I'm going to introduce the panelists, and then we have a set of questions. Stay tuned, ask your question. Hopefully there will be time that we reflect all of them. So our first panelist is Ilana Visby, CEO of Oxford Quantum Circuit, working on superconducting qubit platform. Holds a PhD in physics with a thesis at the crossroad of heterogeneous platform. She's also a champion for women in technology. Next panelist is Tristan Monnier, Director of Research at CNRS Institut Nier in the field of coherent control of individual quantum objects, both in atomic physics and solid-state platform, currently working on controlling electron spin in semiconductor. We also have Adrien Signol, heading the R&D at Pascal, a startup building neutral atom-based quantum processor, PhD in quantum physics, has been continuing research at postdoctoral level, working on quantum simulation with cold atom, also work in Germany, Heidelberg University. And last but not least, we have Zachary Veron, head of hardware at Xanadu in Toronto with 20 physicists and engineering, building a photonic quantum computer, which we will hear more again also later in the day. PhD in physics from University of Toronto, and his expertise is in integrated photonic technology for generation, control, and measurement of quantum light. You see, I'm talking too fast because we have tons of interesting questions to start with. So welcome the panelists. Thank you very much for joining us. Let me start with the burning question that we all want to know, which is scaling qubits. So Ilana, can I ask you to start with telling us the stage regarding strategy to scale superconducting qubit, quality control at scale? Share with us your view, and we continue with the other panelists.
Yeah, sure, absolutely. Of course, it's a really good question, and there's a huge amount of focus and emphasis on scaling quantum computers and scaling the number of qubits that we need to do that. And that's all good and well, but as John, I think, was just talking to, we mustn't rush towards scaling a system stupidly. We can easily build hundreds of qubits today, but they won't be any good, and we won't be able to do anything useful with them. So we do need to be able to focus on scale, quality, and control in order to create high-quality devices that have been designed with that scalability in from the front, from the start. And as you can probably tell, it does get quite complicated quite quickly. So from our perspective, it's really important to make sure that the designs are very simple, scalable, and flexible from the start. And superconducting qubits are particularly good for that because they're so highly engineerable that we can literally design the system exactly as we want for it. That, of course, includes high quality, so high coherence, very low crosstalk, scaling past qubits, the system engineering, as John alluded to. We can't just scale the qubits, we need to scale the whole infrastructure physically. So that we're talking about control systems in a cost-effective manner, as well as the supply chain and ecosystem.
Great. So Tristan, can you also tell us a little bit about the state of art, challenges, and the roadmap for semiconductor qubit? Also maybe silicon qubit, given that you also work with germanium. So the screen is yours.
Thanks, Elam. I want to say hello to everybody first. And as John Martinez said, it is our opinion in Grenoble that scaling is mostly like an engineering issue, okay? And it is clear that there is many things to do to scale our systems in all the systems that exist. But there are, like, as far as engineering is concerned, there are technology that has already demonstrated that they can scale, okay? And this is especially true for silicon spin qubits. The two advantages that I see are clear, and this is potential at the moment. This has to be demonstrated in reality. This is important to say, and this is open question, as Professor Martinez said. But first, the silicon qubits are directly compatible with CMOS technology, which is the only technology so far that has proven to be scalable at very large scale. The second is the ability to work with these qubits at a lower temperature and at higher temperature than the very low temperature that is required, for example, for superconducting qubits. So that means that you can, to control a qubit system, you can embed this QuBit system into like a control system that needs to be implemented at the same temperature that the QuBit system in order to control it efficiently. And at large scales, we know that we need to have this incorporation in order to be practical. So this is the two advantages that I see. And for silicon spin qubit, and it relies on already existing technology, and we are working on this in Grenoble already. We are not the only one, and there are people in Delft or in Intel that are working on this particular aspect to integrate the classical control system to the quantum system.
Does it mean that you can embed a microwave generation at the level of the silicon?
So I think that I don't want to be like to give conclusion now. There are works nowadays that implement at low temperature nowadays generation of microwave field, DAX, ADC, all the apparatus that is known that we use already at room temperature in our system, that we are going to implement using CMOS technology directly on the chip at low temperature. And the point is the fact that if you want to go at large scales, you need to do that. But the point that I wanted to raise is the fact that you need this apparatus are typically like dissipating heat that you need to manage at the cryogenic temperature. So that's a very big challenge, and that's why this particularity of the spin qubit to work not only like at very low temperature but at higher, like 1K. We talk about 1K, where we have like a lot of more power. Cryogenic power than at low temperature. That makes for us like a possibility to embed monolithically on the same chip the classical system and the quantum system.
Okay.
Cool. Okay, maybe we change to you, Adrien. Can you tell us about scalability for cold atom? Maybe you can tell us about the plan for 100, 1,000 qubit that you have and the fidelity of the qubit that we can get with the cold atom.
First, for neutral atoms, the question of scalability is a bit different because the qubits are not manufactured, as it is the case for superconducting qubits or silicon qubits. So our qubits are just individual atoms. So we have for free, let's say, a reservoir with plenty of identical qubits. And now the point is to manipulate them. We use tiny laser beams to trap the atoms. And so in the first approximation, the number of qubits in the processor is limited by the number of these laser beams that we have. And with state-of-the-art techniques, it's already at a high level. It's already on the order of a few hundreds. And for example, at Pascal, we are currently building a 200 qubit processor. Now, it's important to say that with the same technology, pushing forward the few technical limitations, we will be able to reach 1,000 qubits. So we are just starting a new prototype to demonstrate that it's possible. And the plan are to have an industrial version of that running in 2023, so quite soon. And the big challenge now for a neutral atom quantum processor, it's to, of course, to push these numbers up to a few tens of thousands. So we have many ideas, but they're required to develop new technological tools. But what is important to say is that with 1,000 qubits, you have already, you can reach already quantum advantage in many use case problems.
Great. So Zachary, can I ask you to tell us more about universal quantum computing with photonics, especially the CV platform that Xanadu is expanding? You know, what are the challenges in order to expand the depths of computation, spatial architecture? You're looking measurement-based quantum computing. You will hear more about photonic computing later in the day. So tell us about your plan at Xanadu.
Happy to, and good morning, everyone. Yeah, I think the situation with photonics is a little bit different than with the others. Our qubits are sort of more ephemeral objects as they're made of photons, which can be sort of freely created and destroyed, being bosons. So it's a little bit different than, say, manufactured qubits, superconducting circuits, or even things like ions or neutral atoms, which are, you know, physical pieces of matter. So the scalability argument for photonics really comes back to the ability to multiplex, which is quite, I would say, unique to photonic architectures, because we are using these bosonic modes, these photonic modes. We are able to exploit architectures that involve things like time multiplexing, encoding quantum information in sequences of pulses or frequency multiplexing in a single channel encoding a large amount of quantum information in separate modes of different frequency modes of a single optical channel. So that really allows you to scale up in a much more, I would say, realistic manner without scaling up physically quite as fast the actual size of the machine. I think if you look at what happened with classical computation and classical microprocessors, it became clear that there's a need to eventually serialize the problem. Right? You can't really operate on billions of things at once, right? You have to serialize ultimately to say the word size of the processor. You hold a lot of things in memory, but you don't actually operate on that many things at any given one time. So I think the argument of scaling to a fully connected fabric of millions and millions of physical qubits is much more challenging than the situation for photonics, where you just need to create this sort of universal state, this cluster state, and then do measurement-based feed-forward and sort of a very local operation. So the connectivity really just needs to be local. And that allows you to scale up to millions of qubits in principle, which is on our roadmap using our architecture. I will also note that in photonics, I think it actually holds the record for the largest number of independent quantum systems that can be accessed in this manner. If you look at the works out of, say, for example, the University of Tokyo, Akira Furusawa's group, and also recently from Denmark, DTU, Ulrik Andersen's group, where they've managed to create these cluster states in the continuous variable architecture using time multiplexing and access up to, in fact, I think 1 million or more independent quantum systems in the same machine sequentially. So I think photonics has a sort of a unique angle towards scalability using measurement-based quantum computing and knitting together these cluster states using a multiplexing scheme to access many, many more independent degrees of freedom than would otherwise be available.
Thanks a lot for joining at 4 a.m. Toronto time to tell us about photonics. So let me go back to Ilana. We heard the very optimistic view of John Martinez about his view that there is this secret 1 million qubit coming out. We also heard about the IBM roadmap that is recently has been announced. So I'm really keen to hear your view of what you think, where it's going, and what can be expecting of surprises that might come from your startup as well.
Yeah, of course. So you talked about the IBM roadmap there. That's referencing 1,000 qubits around 2023. Already expecting 127 next year, 433 the year after. So you can start to think about the rate of scale, which is incredibly exciting. Wider than IBM and across the space more generally, we have generally seen that huge focus on scale, on number of qubits, and we have been demonstrable increase of numbers of qubits year on year. Even more excitingly, from my perspective, we've also seen almost a halving of error rates every 18 months. And that's a really, really interesting trend, and we fully expect this to continue. We are really nowhere near the limit in terms of coherence or scale, and there's more momentum, more funding, more commercial investment, more partnership. So we absolutely expect this to continue. From OQC's perspective, watch out for the coming year ahead. It's going to be very exciting for us too.
By the way, can you explain us what you are doing with SEEQ, this American company, SEEQC?
Yeah, so as we have a strategy, which is to really focus on building the core, but partner with the best. And SEEQ are part of one of our joint Industrial Strategy Challenge Fund programs, which is government funded by the UK government that we've led. And that's all about building incredibly high quality qubit devices within the UK. And SEEQ are part of that program, and we work with them. They have an interesting approach to digital control.
Okay, so I think we cover scalability. We'll see that if more questions on the chat will pop up and we come back to that. Maybe I let Olivier to take the next question.
Yes, the second topic we would like to cover is how to compare those qubits. And I would like to start with Tristan. What's your views on the way to evaluate the performance of qubits? And what do you think about this famous quantum volume metric that IBM and Honeywell are using right now? Even IonQ, I think, is using it. So how is it relevant or irrelevant to use that metric?
So I will start just to answer your question by reacting a little bit on the quote of John Martinez, who say that basically every system nowadays is interesting. And from a physicist point of view, I used to say that everybody loves his system and wants the system to be the best. Okay, and it's difficult to compare from that point of view. I see as an actor of the field that the engineering community is now asking more and more figures of merit, and this is very good in the sense that that doesn't exclude a platform from another platform. That indicates what platform is going to be good at. Okay, so I think this is really like the spirit of the community nowadays to think in that way. So and one of the figure of merit, of course, is the quantum volume. The quantum volume is telling you just the fact that it is a combination of the number of qubits that you are going to manipulate and the fidelity. Okay, and somehow it tells you like only this I would say more physical properties of the system, and it helps you to compare the quantum computer among themselves. Okay. But for example, if you want to compare it to the HPC computers, it misses completely, for example, the speed of the calculation, which is extremely important. Huh? And so therefore, as any figure of merit, which is giving like a numbers, it is incomplete. Okay. I would add more figures of merit, and basically we used to have this, especially from our engineer colleagues. There are like manufacturing figures of merit, temperature figures of merit, connectivity figures of merit that can be important for the future implementation of quantum algorithm and for the future comparison with the HPC to see if quantum computing is going to be relevant in the future.
By the way, there was a question from online for you directly, is how do you explain that silicon qubit can work at a higher temperature than superconducting qubit?
So it goes back to the very physics, what is at the heart of building the qubit. So the difference between superconducting qubits and the other qubits in general is that superconducting qubits are made of many particles. This is a collective system, whereas the other ones, atoms or spin qubits, are made of only a single particle, like the one electron. So it's a billion of electrons with respect to one electron. And so from that point of view, after that, this is the properties of the qubits itself that is more resilient to temperature. This is just due to the fact that the impact of the temperature is nowadays affecting mostly like the phonon properties of the semiconductor structure that is hardly coupled to the spin. Okay, and for the superconducting qubit, as far as I know, this was mentioned by Professor John Martinez, is the fact that this quasi-particle that can basically be an issue in the quality of the qubit are more and more important as you increase the temperature. So that's why basically using spin degree of freedom usually protects you from any kind of electrical charge and therefore allows spin qubit to work at higher temperature, which has been demonstrated in several experiments recently.
Thank you, Tristan. Back to Zachary. Same question. I mean, how is quantum volume relevant in the case of photons? It's probably, you may need different figures of merit to compare those qubits, I presume. So can you explain how would you define the performance of the types of qubit you are working on?
Yeah, I'd agree that quantum volume is probably not so useful for present-day photonic quantum computers. I have a personal opinion that I think quantum volume is very useful for comparing architectures that are identical, and that's even within fixed physical substrates, or even within superconducting circuits, for example. I would advise using quantum volume more to compare the progress of, say, a given company or a given research group in advancing their same architecture than even comparing two slightly different architectures within one physical approach. And so certainly outside of that physical approach, I wouldn't apply quantum volume. It's especially inappropriate for a lot of NISQ era application kind of specific quantum circuits. For example, at Xanadu, we have our first products now available on the cloud, our X series quantum processors. These are Gaussian boson sampling chips. And so these are not actually at all analogous to, or cannot really be simulated or not equivalent to the other existing cloud deployed quantum computing processors, because they use a completely different architecture, a completely different set of physical degrees of freedom, and the application space that they address is completely different. So we really rely on more native metrics for photonics. How much loss do you have in terms of these near-term devices? How large is the system? How strong in our case is the squeezing parameter? That's a physical parameter that quantifies sort of how many photons are generated, and the utility, the noise level. So really more kind of in situ physical metrics like that, I think, are still much more useful. And then ultimately just algorithmic performance, I would say, is going to continue to be maybe the more useful benchmark to compare very, very different approaches. How well do you perform at a particular task?
Thank you, Zachary. Moving to Adrien, I would reframe the question in a different manner. What kind of benchmark tools are you using to evaluate the performance of your own qubit right now? Given you can use it in two fashions, I mean, quantum simulation and quantum universal gates programming. So how do you make sure you have a good way to evaluate the performance of these qubits?
Yes, that's a very interesting question. Also, because it's related to the problem of certification of a quantum processor. Clearly, it's difficult to find quantities that are relevant for any types of architecture or that are hardware agnostic, basically. At Pascal, we are seeking for comparison procedures. And for example, we are trying to develop an equivalent of the randomized benchmarking that has been mentioned by John Martinez in his talk, but for analog processing instead of digital. So it will somehow characterize how well quantum Hamiltonians can be implemented in the processor instead of how well quantum gates can be implemented. So we are trying to develop such approach to put numbers, but to characterize how good is our processor. But clearly, the difficulty comes from the fact that the processor are sometimes more appropriate to solve certain types of problems than some others, and so at the end it's difficult and to have just a few numbers that characterize it, and in that sense, all the processors are not fully comparable and not so easy to certify numbers or to have a clear diagnostic.
Okay.
So just before I go to the new question, there is a question in the chat. Maybe, Ilana, I ask you, given your heterogeneous background about various qubit, to answer that. So the question is that one of the most challenging issues for quantum computing is the storage of information. How different type of qubit compare vis-a-vis this issue of the memory?
Yeah, sure. So I basically put it in the sense that lots of different qubits have advantages and disadvantages across different ways. So if you're looking for quantum storage, then yes, you will want long memory time, so long coherence time. So certain qubits would be more well suited for quantum storage for quantum memory. And you said that there would be other different examples of that. So if we start to then think about what a hybrid quantum computer might look like, you might see different components with hybrid systems across platforms that are best suited in the same way that classical computers, have different GPUs for different purposes.
Okay, thank you very much. So let's change the question to application, my favorite topic. So we can think about different platforms, as Elena just mentioned, that depending on what you want to look at them might be also more suitable for different applications. Maybe Zachary, you can tell us, because Xanadu has also this very strong focus on QML and using CV for the quantum machine learning. So what's your view about existence hardware being already employed in algorithm and application, and the way of comparing again or suitability of different platforms for different applications?
Yeah, thanks. That's a great question. So for photonics, I think it's a bit of a unique situation because we use, again, back to these, using a very different physical sort of degree of freedom, these modes of light. It allows us to access a space of problems that's not accessible to, I would say, the conventional qubit model of, say, these two-level systems. So because we use harmonic oscillators, infinite dimensional Hilbert spaces, we can encode problems that are very, very different than other approaches. In our architecture, you mentioned quantum machine learning. That's one. It's sort of a very natural mapping between neural networks and the architecture of our chips, in which sort of the weights in a neural net can be directly mapped to the weights in phases in our chip, in our linear optical circuits. But I'd like to focus a little more on graph structured problems. Over the last couple of years, our research group and others around the world have shown that in using this photonic encoding based on squeeze state, based on this continuous variable model, it turns out that you can embed graph structure data and represent it very, very well. So graph structure data meaning data that can be represented as a bunch of nodes connected by edges which have weights associated with them. A lot of different problems can be represented this way. It turns out that can be very naturally encoded in our machine, and you can learn interesting properties about these different graphs that you can encode from these statistics of the measurements that you carry out on the system after the graph has been encoded. So this touches all sorts of industries. For example, in chemistry, you can encode the molecular structure of a molecule and study its vibronic spectrum as it undergoes transitions, electronic transitions. How does its structure change in the vibrational modes? It's a very natural mapping there. And actually, we have managed to successfully do some sort of toy problems in that architecture. And there are others you can use. You can use the architecture to study the similarity between different types of graphs to try to obtain a distance metric between different graphs, something that's conventionally quite hard to do with classical computation. So I think we'll see a lot more of these more kind of mathematical problems embedded. I would say for all approaches, photonics included, we still are at the era of really near-term toy models, so toy problems. The size of the system and their performance is such that you can't not yet, I would say, obtain a quantum advantage in really any architecture. But I think for, again, photonics and also all other architectures, we'll start to see in the next 2 years or so that boundary being crossed, and where the scale of the system and the performance becomes good enough such that some of these problems, including hopefully some of these graph structure problems and chemistry problems, can actually obtain maybe a debatable, but at least come closer to showing a genuine quantum advantage and become useful for sort of real enterprise applications. I think the real battleground for that will be in the next couple of years.
Thanks a lot. And similar to that, also maybe Adrien, we can talk about quantum simulation, which is again another special thing built up for cold atom. We know that this is the great. So maybe you can elaborate a little bit of this, the suitability of cold atom, both for universal computation, but as well as quantum simulation. And that road, how it helps with all the question that we say, fidelity, scalability. So suitability of application of cold atom.
Sure. Yeah, so indeed, cold atoms are particularly well suited for quantum simulation applications, I think, because they are very versatile in terms of geometry, dimensionality, in terms of control of the interactions between the qubits. So all these tools allow to mimic complex quantum phenomena that take place in many areas of science. For instance, we are very much interested at Pascal in question of magnetism in solid-state materials, question of reactivity of molecules in quantum chemistry, and we really want Pascal to be or to foster scientific discoveries in these fields. But it's not only, as you said, it's not only quantum simulation. It's also quantum computing that we can do with cold atom quantum processor. I think there are a lot of classical problems that can be addressed as soon as you have a number of qubits, like 1,000 qubits, as I mentioned before. We are, for example, focusing on problems like finding approximate solutions to nonlinear differential equations or solving hard combinatorial optimization problems. Maybe there is one example that I found very illustrative about that. It's a project that we're running with EDF, the French electricity company. So they have a very concrete problem, which is how to optimize the charging of an electric vehicle fleet. So they figured out that this can be mapped into a graph problem, something that is well known but is also very difficult to solve classically. And instead, there is a large computational gain if you implement this graph problem into a quantum processor based on neutral atoms. So that's this kind of applications that we are interested in, that we are developing in our company. And at the end, if you are able to solve this problem, it's not that you can just solve one specific problem. It's a whole class of applications that you might be able to solve with your processor.
Okay, so now we're going to move to the last of the 4 topics we wanted to cover. It's about the qubit complementarity, because there are many architectures where you may need 2 different kinds of qubit to achieve a useful system. And we actually had 2 questions from the audience about QRAM, I mean quantum memory. So who would be volunteering to talk about the kinds of technology that we would use for quantum RAM, quantum memory, that may be different from the types of qubit you are using yourself? Who is volunteering to answer this question? Can it be Ilana, Adrien, whoever, Zachary? Big silence. I will ask Ilana, for example, maybe.
Yeah, that's fine. I thought I'd give someone else a go if they're interested. So for quantum memory, you do want to look at that long coherence times. And if you start to think about potentially up-down conversion, you want to look at what could integrate, for example, and start to see different places. So for the quantum memory, you might want to use that for a conversion piece. So you might look at converting something from an optical into a microwave signal. So for quantum memory, for example, they're looking at spin systems. They're more isolated from the environment, so they have longer coherence time, but that means that you can't access them so quickly. But you're looking at memory, that's much more important, is to have the longer coherence times. It doesn't matter about the faster processing speeds.
So who would be the best candidate for memory complementary to superconducting qubits? You mentioned spin. It's NV centers or something else?
Potentially. I think it's always, I would hark back to some research I'd done previously, actually, which is starting to look at different ions where you might be able to then have within the band structure beneath them optimized different signals conversions. So I think that's always really interesting, because then you could start to think about having signals that convert between both microwave to optical. And for that, looking maybe potentially at different molecules, different underlying ions are really interesting. But of course, Michelle Simmons, world-class, incredible research out there. So I think a partnership between those 2 technologies would be very powerful.
Excellent. Another similar question for Adrien and maybe Tristan as well. So do you plan to use photons as a way to complement cold atoms as well as silicon qubit, at least for communication or intercommunication between 2 processors?
For scalability.
And for scalability, yeah, of course, yeah.
Yes, I will say at the moment, in the short term, we are using photons only to manipulate the atomic qubits. But in a longer term, indeed, it can be interesting also to develop the photonic approach, and the interface actually between the atom and the light is something that is very promising. There are lots of work to develop also these quantum memories that we were talking about, implementing, encoding, I would say, the information from the photon into the atoms. So for sure, it's these are interesting perspectives for us in order to extend the possibilities of our processor. But this is much more for the long-term perspective, I would say.
Okay, Tristan, same question for you.
Yeah, I will go along what just Adrien said about the fact that you have to realize that it is still a matter of, I would say, like as we say in French, fundamental research. So there is demonstration to do. The systems, the hybrid systems are not mature enough nowadays in order to be potentially implemented into like an architecture. So this is good. This is exactly what Cedrico said, is the fact that we are not, there is place for like something which is more going to the market with like something which has been already demonstrated. And this is more like an engineering work to assemble the qubits together. And also like other type of functionalities that can be investigated in a more fundamental way to demonstrate the fidelities that we need to incorporate them into like a quantum architecture.
Thanks, Tristan. And Zachary, you're the last one on this topic. So can you be self-reliant using only photons, or do you need other technologies for intercommunication or whatever, complementary technology around your QMod qubits?
Yeah, definitely. So that's one of the, I guess, real advantages in photonics is that you're already in the photonic domain. So interconnects like that are no problem. I would like to just point out regarding the memory discussion, QRAM is not the same as quantum memory. Quantum memory, could refer to just long-term storage or quasi-long-term storage of quantum information, whereas QRAM is about coherently in superposition, potentially accessing, addressing that memory. So I think that's an much more difficult problem. So I would say it's important to have an architecture that does not require QRAM because it's extremely difficult, and I think luckily there are many architectures that do not. The other, I would say, is for memory, for sort of more medium term, just simple storage and retrieval, not coherent, just simple storage and retrieval of quantum information. Currently, the best memory is an optical fiber, a spool of optical fiber. It's effectively a delay line, a buffer. And for that, the nice thing about photonics is that it's already there. You have some quantum information, you switch it into a fiber or an on-chip waveguide spiral, some kind of delay, and then you can retrieve it quite readily insofar as it hasn't been lost. So you do have to get, obviously, coupling losses and propagation losses down. But it's in a sort of a native innate compatibility with the photonic technology. There's no need to transduce between two different domains to achieve a sort of a simple quantum memory like that.
Okay, great. We have 1 minute. Anybody who wants to type in the chat, you have a chance. We'll ask the question. I can quickly repeat that people were very excited about this hybrid possibility that Ilana was mentioning and everybody commented on. And I guess maybe if anybody has anything from the panelists, we would be glad to have it. And thanks again very much for joining for this very exciting QuBit roundtable.
Thank you very much. Have a good day or night.
Or morning.
Morning, whatever. Yep.
Thank you.